So let's do a brief review of our kinematic equations. Displacement, which we represent with delta x, where delta is the change and x is the symbol we use for position. So our change in position is equal to our final position minus our initial position. We can figure out the position at any given instant in time, assuming we have a uniform acceleration. So our final position is equal to our initial position plus our initial velocity times time plus 1/2 times that uniform acceleration times the time squared. This is an equation for position as a function of time. This is the equation that we ended up figuring out at the end of our ramp lab. Now, velocity, we defined as the slope of a position versus time graph. Now, assuming it's a constant velocity, it can be the change in position over the change in time. Otherwise, we write it like this, dx over dt. So that instantaneous rate of change of position as a function of that instantaneous rate of change for our time. Now, we also have an equation to figure out velocity at any instant in time, once again, assuming a uniform acceleration. So this is going to be our velocity is equal to our initial velocity plus that uniform acceleration times time. Our acceleration is defined in much the same way our velocity was. It is defined as the slope of a velocity versus time graph. We can also figure out another way of solving for velocity, but this is not velocity as a function of time, but rather velocity as a function of displacement. But this equation can only be used, once again, if we have a uniform acceleration. So our final velocity squared is equal to our initial velocity squared plus 2 times that uniform acceleration times our change in position. These are all of our kinematic equations we've been using for linear or translational motion. However, each and every one of these equations we can also write in terms of the angular or rotational variables and use those equations in exactly the same way. So our angular or rotational displacement is the change in theta, that symbol we use for angular position. So its change in our angular position is equal to our final angular position minus our initial angular position. We can do the same thing with our angular position as a function of time. Our final angular position is equal to our initial angular position plus our initial angular velocity times time plus 1/2 times our uniform angular acceleration times time squared. The slope of an angular position versus time graph is our definition of angular velocity. Our angular velocity as a function of time can be calculated with angular velocity final is equal to our initial angular velocity plus our angular acceleration times time. Our angular acceleration is defined as the slope of an angular velocity versus time graph. And then our angular velocity as a function of displacement graph is going to be solved as our angular velocity final squared is equal to our angular velocity initial squared plus 2 times our uniform angular acceleration times our angular displacement.